Okay, we're going to talk now, we're going to hear about black holes. We cannot directly see them, but when we're told to crash into each other, they emit the gravitational waves. I think we all know that. We've heard of things like this, and they can be detected by the observatories LIGO and Virgo. Tonight we're going to learn how LIGO's upgraded gravitational wave interferometer works with the advanced Virgo net detectors over in Tuscany, over in France, and it was funded by France and Italy. Our speaker tonight is Dr. Maya Fishbach here. She's a gravitational wave astronomer. She's currently working at CIERA, Northwestern University, and funded by the NASA Hubble Fellowship Program. She's got a BA in math and physics she earned at Yale. She was an NSF graduate research fellow at the University of Chicago, where she completed her PhD in astronomy and astrophysics. She's also a member of the LIGO Scientific Collaboration. So let's welcome Dr. Fishbach. Should I turn some of the lights off?
Probably so.
Yeah, so thanks everyone for being here, and I'll tell you a bit about what we can learn by listening to these black holes, or basically doing astronomy with gravitational waves, which is what I do. So in today's talk, I hope to just cover a few things. So one, what are gravitational waves? Two, how can we observe them with LIGO and Virgo? And three, a bit about what we can learn from these gravitational wave observations. So I'll start by talking about the first direct detection, which is old news by now, but I think it's still really amazing. So the first direct detection actually happened the same month that I started graduate school in September of 2015, where the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected gravitational waves for the first time. And these gravitational waves originated from two black holes a billion light years away, and that really gave birth to a new field of astrophysics, which really lucky for me because that's exactly when I started my PhD, so I was able to do my PhD on gravitational wave astrophysics and cosmology. So what we detected in September of 2015 was two black holes, each around 30 times the mass of the sun, and we always detect black holes in pairs, because what we detect is two black holes that are in this binary, they're gravitationally bound to each other, and they're orbiting around each other, they're going around each other, and you can see that they're actually getting closer and closer together. And that's because they're losing energy in gravitational waves that are being radiated out from this source. And so they're getting closer and closer together, and eventually they merge and form this bigger black hole. And this happens, these last few seconds of this event is what we're able to observe in gravitational waves. So what we had in this event are two black holes that are crashing into each other, moving at over half the speed of light. So moving very, very quickly. They're each 30 times the mass of our sun, so they're also quite big. They have a lot of gravity. And they merged about a billion light years away. And those gravitational waves then traveled through us. This event emitted more energy than the entire rest of the universe combined in gravitational waves. So it wasn't energy that we could see, it wasn't this explosion that we could see in light, it was just this energy in gravitational waves that traveled to us and we were able to detect. So when this happened, it was a pretty big deal. It made the front page of the New York Times. You can see here, this is the detector. And hopefully by the end of this talk, you'll get some idea of why it was such a big deal. So what is all the excitement about? Well, so the first thing that we learned is that gravitational waves actually exist. And so Einstein's theory of gravity is correct in this way. For the first time, we were able to test that. And the second thing we learned is that there were actually these systems out there, that there were actually black holes that merged in the universe, which we had no way of knowing before. And it's a new way to observe the universe. So what are these gravitational waves? So this is Einstein as a quite young man in around 1915 when he wrote down his theory of gravity. And this theory of gravity is general relativity, which tells us that space and time are inextricably linked in this fabric of space-time. When you have massive bodies on that space-time, they curve space-time. So that's what you can see here in just this cartoon illustration is this fabric which has this grid on it. You can see that you have a massive object like our sun, and that causes the space-time to curve. And what this curved space-time does is it causes other objects, like the Earth here, to feel gravity. So they react, they move according to that curvature. And so gravity is actually just the bending of space-time. It's not a force like we might think of in Newtonian gravity. It's actually just the geometry of space and time. So when we feel any kind of gravitational attraction, it's actually just that there's some curvature of space-time and that we're moving according to that curved space-time. So one way of summarizing this is that space-time tells matter how to move and matter tells space-time how to curve. So it's this feedback, it's this back and forth between matter, anything that has mass is affecting space-time and causing this curving, and then also moving in response to the space-time of the curvature of other objects on that effect. So now what are these gravitational waves? Well, one way of thinking about gravitational waves is that anything with mass, so I have mass and I'm causing space-time to curve, but now I'm moving, and my movements are causing space-time to curve in a different way. It has to adjust because I'm a moving mass. But how does that information get carried out to other masses in the universe? We know that information can't travel faster than the speed of light. How do you, a nearby mass, know that the curvature is different? Well, that information gets carried as gravitational waves. So gravitational waves are a way of communicating across space-time that the masses in the space-time are in a different configuration. So extremely massive objects moving at extreme speeds are causing ripples in space-time. And actually, any masses moving at any speeds, like in the example where I'm shaking my arms right now, are causing gravitational waves, but they're really, really tiny. So in order to have any noticeable ripple in space-time, we need to go to these extremely massive objects that are moving very quickly. And they're causing these ripples in space-time, which you can think of as waves in a pond. So if you drop a pebble into a pond, it'll cause these ripples that travel out across that fabric of the surface of water or across the fabric of space-time. And you can think of gravitational waves as these ripples. So what do these ripples do as they're actually traveling across the universe? Well, here's a little movie that shows if gravitational waves passed over the Earth in a very exaggerated way, because gravitational waves are passing over the Earth all the time. And what you see here, so these gravitational waves are now hitting us, and it causes the Earth to kind of wiggle a little bit because these gravitational waves are these ripples. They're causing this wiggling of all of space-time, including the surface of the Earth. So what they actually do, the way that we can measure that they happen, is that they cause things to move. That's basically the effect that we're measuring when gravitational waves are passing through. They stretch and squeeze things a little bit, like you saw in the kind of jiggly Earth. And one way to imagine this is imagine that I set up these rings of test masses. And what I mean by test masses is assume that these little masses are so small that they don't really have an effect on each other. And I set them up in this ring, and now I send a gravitational wave through the screen. And what this gravitational wave does is it will cause this ring of test masses to stretch and squeeze. So you can see that these little test masses are actually moving farther and closer together as they're being stretched and squeezed by this gravitational wave. And this effect is really, really small, but that's what we're able to measure. You can also see that the test masses that are further away, apart on opposite ends of the circle here, are moving more from each other. So gravitational waves are causing this relative changes in space-time. If you have two test masses that are very far apart, they end up moving a greater distance. And another way to see this, because these gravitational waves are actually propagating through space-time. So here now, imagine that I have a bunch of rings of test masses behind each other, and then a gravitational wave passes through. And so you can see that there's this wave of space-time stretching and squeezing. And that's what this gravitational wave is. It's moving through space-time. It's actually traveling at the speed of light, and it's causing objects, any masses, to stretch and squeeze. So I said a couple times already that gravitational waves are really, really weak. So the gravitational waves that I'm causing right now by moving my arms around are really weak, but even the loudest gravitational waves we can imagine are extremely weak. And what I mean by weak is that the distances, so they're causing space-time to stretch and squeeze, they're causing distances to change, the distances between two masses to change, but that change in distance is really, really small. So the loudest gravitational waves that are in our universe are only changing the distance between our sun and the next closest star, which is 4.3 light years away, by the width of a human hair. So it's a tiny, tiny change in distance. That means that any distances we have on the Earth, if we have two test masses on the Earth like we have in our detectors, that change in distance is less than an atom in width. So it's really, really tiny. So that's what I mean by gravitational waves being weak. So that means that they're really hard to detect. And in order to detect gravitational waves, we need two things. We need a really loud source of gravitational waves, which you can imagine here as this speaker, and a really, really precise detector. So this microphone that's just listening for gravitational waves. That's really precise. So I'll start by explaining what some loud sources of gravitational waves are. And you probably already guessed because I started off talking about black holes, and black holes are in the title of my talk, but merging black holes produce really loud gravitational waves. Neutron stars, which I'll also explain a little bit, also produce loud gravitational waves. So you have two black holes, and this is similar to the movie I showed at the beginning, and they're orbiting around each other. They're causing these ripples in space-time, or these gravitational waves, as they're getting closer and closer together. And so these gravitational waves are now traveling out from this merger of two black holes and travel out throughout the universe until they reach us here on Earth billions of years later. Okay, so what are these black holes? Well, many of you probably saw this picture, which I think was released a couple of weeks ago or so, from the Event Horizon Telescope collaboration. So this is actually a picture of a black hole. It's not any of the black holes that we've detected in gravitational waves. This is the black hole that's at the center of our galaxy, the Milky Way. And it's millions of times the mass of our sun, so it's much more massive than any of the black holes I'm talking about. But other than that, it's the same thing. Black holes are really, really simple. Black holes are just these regions of space-time where you have mass pushed into such a small region that it's so, so dense and nothing can escape from it. So that means that if I'm standing within the black hole and I'm shining my laser pointer upwards, that light from my laser pointer is never going to be able to escape the black hole. So they emit no light. What you're seeing here in this picture is all of the stuff that's around the black hole. So it's this gas that the black hole in the center of our galaxy is eating, but it just gets really, really close to the black hole. You can't actually see any light being emitted from within the black hole because it's a black hole. So these are the densest objects in our universe, and they're completely dark. Neutron stars, on the other hand, you might think, oh, they're kind of more boring than black holes because they're a little less extreme. They're kind of the less dense cousins of black holes, but they're still unimaginably dense. They're denser than anything that we can imagine here on Earth, and they're actually made up of stuff. So they're made up of stuff that's squeezed to such high densities that it becomes this very extreme matter, and they're not dark. So they're made mostly out of neutrons, like the neutrons that we have inside atoms, that's just squeezed into very high densities. So they're kind of these city-sized stars. If you took a neutron star, they're usually around 1.5 times the mass of our sun, and they comfortably fit within a city. They're like 10 kilometers across. And here's an image of a neutron star, this little blue point here, inside this explosion. And this brings me to how neutron stars and black holes are made. Well, we think that one way, at least, that our universe makes neutron stars and black holes is through massive stellar evolution. So that's really cool because these black holes and neutron stars that we're observing are the skeletons of very massive stars. And so we're actually looking at this graveyard of stars by observing all these neutron stars and black holes. So what I mean by this is that if you start off with a massive star, by a massive star, I mean a star like our sun, but 10 or more times bigger than that. So probably a lot of the black holes that we're observing are made from stars that are 100 times the mass of our sun when they're born. And these stars, during their life, they're shining. The way they shine is through nuclear fusion. They're taking hydrogen, they're smashing hydrogen atoms together, turning that into helium, releasing a lot of energy that's allowing them to shine. And then they turn helium and mash it into carbon and oxygen. And they keep going up the periodic table, making heavier and heavier elements until they get to iron. And when you have iron in your star, because of the way chemistry works, you can't mash iron together to make heavier elements and release energy. So at that point in a star's life, it can no longer make enough energy to sustain its shining. And what happens often is that the star then explodes. It goes supernova, and you have this explosion, and what gets left behind, if it's a very massive star, is a neutron star, and if it's even more massive, it's too much mass squeezed into too small of a region, you get a black hole. And so it's this very dramatic life that these stars live, and it actually is very short. So these very massive stars are very short-lived. It's hard to catch a glimpse of them during their life. But they form these neutron stars and black holes that just hang around our universe forever. And so this is a great way, if we can find a lot of these neutron stars and black holes, this is a great way of actually learning about the lives of these stars. Okay, so the gravitational wave signal from these mergers of neutron stars or black holes looks something like this. So the gravitational wave here is being plotted the amount of stretching. So this amplitude, the higher up it is, there's more stretching, and then it goes across time as it sweeps across our Earth. And so you see here during the earlier parts of the evolution, it's called the inspiral. You have these two black holes that are orbiting around each other, And then the gravitational wave frequency is twice the orbital frequency. So when the black holes are far apart and they're moving kind of slowly, the gravitational wave frequency is pretty low. But then these black holes are getting closer together, they're starting to orbit each other faster, and so the gravitational wave frequency is also increasing. And then finally, the two black holes get so close together that they merge, and there's this corresponding spike in the gravitational wave amplitude. And then you have this final black hole that rings down, so it's kind of shedding off any additional imperfections and just settling into this perfectly spherical black hole. And that's this dying down of the signal here. It dampens away, and then there's no more gravitational waves.
So question?
Yeah.
So if you were to continue that curve, would it just be a flat line?
Yes, for the most part, it would just be a flat line. It might actually be a little bit displaced and upwards, so it would be flat, but it might be a little bit higher than the flat line you started off here. That effect is called gravitational wave memory. It's really cool. It just means that space-time actually can remember previous gravitational waves that have passed by. But yeah, there's no more oscillations. Yeah.
What's the wavelength?
So the frequencies here, so it depends on the masses of the objects. So the bigger black holes are further apart, and so they are lower frequencies or longer wavelengths. The gravitational waves that we're sensitive to, and so the ones that we're observing, are between 30 hertz to 100 or so hertz. Yeah.
Yeah. So most of these images are showing two objects. Are we capable of seeing anything with more than two objects, or does that happen? Do we know if it happens?
Yeah, so we've only ever detected like two, like this kind of binary inspiral. We know that there are systems out there where you have triples, so like 3 stars. Usually what would happen is that you have 2 of them are closer together, and so they're merging first. It's also possible that sometimes you'd have like a head-on collision. That would be a lot more difficult for us to detect because we're really looking for something like this. But yeah, we're usually, even if you have a triple, there'll be like some inner binary that is merging first, and you have some outer triples. You can separate the problem like that. It's possible that rewinding this, if we could detect the gravitational waves where you have a kind of more comparable distance between the inner 2 and the outer one, that there would be some effects of the third companion on the gravitational wave, but that would require us to be able to observe these further back in time before merger, which we could do by getting sensitivity at lower frequencies, for example. Yeah.
So if you had 3, would you get sort of a Fourier summing of the waveforms to get a kind of non-symmetric waveform?
Yeah, that's an interesting question. I think if you had 3 where really all 3 were contributing at similar levels, you definitely have something more complicated in the waveforms. I'm not exactly sure how. I think probably at earlier times, so further separations, you would be able to approximate it as kind of split up the problem like that. But the 3-body problem is really hard in just normal gravity, and general relativity makes things even more complicated. So yeah, not totally sure. Okay, so what this gravitational, we often talk about these gravitational wave signals as these chirps. I'm not sure you'll be able to hear my audio. Can people hear that? I could hear that. But anyway, so I showed you this. This is the amplitude, how much stretching there is as you go across time. If you look at the frequency of the gravitational wave as a function of time, you see, and the brightness here corresponds to the power and the gravitational wave signal. At these early times, you start off at these low frequencies, and then as you sweep across time, the frequency of the gravitational wave increases as the black holes get closer together. And the amplitude of the gravitational wave increases as well. So you start off with something kind of quiet at low frequencies, and then move on to something that increases in volume and frequency, and so that sounds like a chirp. And because of these frequencies that we're sensitive to, it actually is similar to the frequencies that our ears are sensitive to. So it really, you can really put these signals in sound waves, and it sounds like, could people hear the chirp? Yes, okay, cool. Yeah, so I really like this cartoon from the New Yorker, these two birds saying, was that you I heard just now, or was it two black holes colliding? Okay, so this brings me to how do we actually detect these gravitational waves. And we have this worldwide network of interferometers, which is what our detectors are, that are listening for these gravitational waves from across the universe. So this is the equivalent of the microphone in that visual I showed with the detection prerequisites. We need a really loud source, but we also need a really sensitive microphone, essentially, to listen for these gravitational waves. And so our network of gravitational wave detectors is these two LIGO detectors in the US, one in Washington State and one in Louisiana. And then you heard in the introduction about the Virgo detector in Italy. There's also a detector in Japan called CIERA, which is really when our detectors turn on again, CIERA will also join LIGO and Virgo in listening for gravitational waves. And then there's also a detector that's planned for India called LIGO India, which should come online and join this network sometime later this decade. So the way that these detectors work is through interferometry. What that means is that we have this. So you can see here in these pictures that all of these detectors consist of these two arms, these two tunnels, and there's lasers that travel down these arms. So in this movie that I'm about to show, these are those two arms, and we have these test masses at the end of the arm. So similar to that ring that I showed of test masses where the gravitational wave passes through and that ring is stretching and squeezing. In this case, these test masses at the end of each arm are mirrors. And so you have these lasers that travel down each arm and bounce across from the mirrors. And let me just pause here. So when a gravitational wave passes overhead this detector, it's causing the distances to change. Space-time is stretching and squeezing. And so as a gravitational wave passes overhead the detector, those two mirrors at the end of those tunnels are moving. One arm is getting a little bit longer, the other arm is getting a little bit shorter. And the way we measure that is with these lasers, because you can't just put a ruler and try to measure how long the arm is relative to the other arm, because the little marks on your ruler are also going to stretch and squeeze as space-time is stretching and squeezing. So what we use is the fact that light always travels at the same speed. So we can measure the lengths of these arms by measuring how long light is taking to travel there and back. And as the gravitational wave passes by, movie, one arm is getting a little bit longer while the other gets a little bit shorter in this pattern. And what this does is cause this interference pattern, because this laser light is itself a wave. So as it travels down and gets reflected, while the other arm, it's also traveling down and gets reflected. If there's no gravitational wave, the two laser beams kind of cancel each other out in this destructive interference, so there's no signal, there's nothing in the output. But as a gravitational wave passes through, one arm gets a little bit longer and the other gets a little bit shorter, and so that causes this interference pattern as the laser lights recombine at the output, that we're able to essentially measure this pattern of how much did the distances between the arm change at what frequency. So that's how we detect these gravitational waves in all of our detectors. And these detectors are really amazing. I said earlier that all of these gravitational waves that our universe is producing are really weak, and so we have to be able to measure these distances that are smaller than the width of an atom. And remarkably, we actually are able to do this. So we now have all of these detections in this gravitational wave transient catalog. You can see that each one of these panels contains this chirp, which is the gravitational wave signal from two black holes or neutron stars merging. And we have around 90, depending on how you count, there are around 90 of these detections observed so far since 2015. So the vast majority of these are from two black holes, but there are also a couple of these events that involve two neutron stars, and even a few of them have a mixed merger between a neutron star and a black hole. So another way to visualize our catalog is with this little cartoon movie that my colleague Zohair Doctor made. And here, each one of these little panels now here shows corresponding to these chirps is the actual system that caused it. So these two black holes or neutron stars orbiting around each other. You can see just from here, you can get a sense of how different sizes we have of these objects. So we have these really big black holes over here. It's really hard to see their little blue points over here. These are two neutron stars. So we have a wide variety of these events, and for the next few slides, I'll try to explain what is all the astronomy that we're able to do with having all of these events. Yeah?
So when two neutron stars merge, they create another neutron star, right?
So it depends. Usually, if you have two neutron stars merge, there's a maximum mass to a neutron star. So there's an upper limit to how much mass you can add to this neutron star before it will just become too heavy and collapse to a black hole. And so if you have two neutron stars merge, they often will give you something that's above that mass. So it will usually collapse to a black hole after some time. Basically, and yeah, that time scale has to do with if you have a rapidly rotating neutron star, it can support a little bit more mass. So if you have this merger of neutron stars, if it's rotating really quickly, it might take a tiny bit longer to collapse to a black hole, but that's exactly how that happens, and what the gravitational waves look like from that process of a heavy neutron star collapsing to a black hole is really interesting and something that we haven't detected yet. Yeah.
How did you decide on the length of the arms and the interferometer?
So for the LIGO detectors, those arms are 4 kilometers long. For the Virgo ones, each arm is 3 kilometers long. It's it's cheaper to make arms that are shorter, but the longer the arms, the more sensitive the detectors. So these are good length arms and that they are detecting gravitational waves. There's actually a plan to construct new detectors for like the 2030s, around 10 to 15 years. Hopefully, it's still kind of in early stages of the planning for these new detectors, which will be the successors to LIGO and Virgo. And the plan is to actually have 10 times longer arms, so 40-kilometer arms. And that will allow you to be even more sensitive because, right, we're detecting these relative changes in distance. So the longer arms you start off with, the same relative change in distance is now 10 times more distance. So it helps to have bigger arms, but it's more expensive. And actually, when you get to 40-kilometer arms, whoops, got too excited about big arms. When you get to 40-kilometer arms, then you have to worry about the curvature of the Earth, like you want something flat. So that it comes with a lot of extra challenges when you try to go bigger. Yeah. Okay, so in order to really do science with these gravitational wave detections, we have to analyze the signal. So we detect it, we have these chirps, but we can actually learn from the gravitational waves what it is that we're listening to. And so these gravitational waves are telling us about these sources. The first thing they're telling us is how big each black hole or neutron star is. So right, we're always observing these events. We're always observing these black holes and neutron stars in pairs. So we have these two masses, primary mass and the secondary mass. We can also measure from the gravitational wave signal how fast those black holes or neutron stars are spinning. And so that's what's denoted here, are their spins, and also where are those spins pointing to. So in general, black holes and neutron stars are rotating, and they can be rotating either in the same direction as the orbit, or they can be rotating lopsided in the plane of the orbit. So that can tell us a lot about the origins of these systems. We can also measure where that these sources happen. So where on the sky did this merger occur? And that's a main reason why it really helps us to have so many detectors. So you might have seen, I showed this map of the world with all these detectors, and you're like, why are there so many? Well, one reason it's really helpful is it helps us to know that something is real and actually coming from the universe if two detectors are observing the same signal at the same time, or the same time modulo light travel time between the detectors. Otherwise, it is really hard to tell if this is a real gravitational wave signal coming from outer space, or is this just the ground shaking a little bit because a truck drove by. So that's one reason it helps. The other reason it helps is that it allows us to have a much better idea of where on the sky did this merger happen. So usually these gravitational wave detectors really are like these microphones. They're just picking up everything. They don't really have sensitivity in like a particular direction. We're not pointing them at a particular area of the sky. But when we have a lot of detectors, we're able to triangulate and have a better sense of where on the sky the source is coming from. So we can then look and see, what galaxies are in that area. We can also tell how far away the merger happened, which helps us figure out when we're looking further out in the universe, we're looking back in time. By figuring out how far away is the source, we can learn how long ago did it merge? How old was the universe when this merger happened? And that can help us figure out how do these events that we're observing tie into the evolution of stars and galaxies in our universe. And the other thing that we can learn from the gravitational wave signal is in the case of neutron stars, black holes are only described by their masses and their spins and the geometry of where the merger happened. But in neutron stars, there's additional information because they're made out of stuff and they are squishy. And how squishy they are is going to affect the gravitational wave signal. So we can learn something about what neutron stars are made of by measuring how they're reacting to being with another neutron star and how that's affecting their gravitational wave emission. So just a couple of examples of what we're able to learn. So this is a plot that is from a recent paper that we wrote within the LIGO Virgo CAGRA collaboration. And what we do in these papers specifically is look at the astrophysical population of black holes and neutron stars. So look at things like all the masses of the black holes that we've observed. Can we look at how many black holes, so what is the merger rate of black holes, as a function of their masses in solar masses? So you can see here that we just take all the masses of everything that we've seen, and from that we infer that it looks like there are a lot of black holes that have small primary masses, that these light black holes are more common. And then as we get to heavier black holes, there's a smaller merger rate. But we're also starting to see some features here. So we can start to look at, okay, where does the black hole mass distribution start? How small is the lightest black hole in the universe? And how does that compare to the heaviest neutron star? Is there kind of this smooth transition between maybe you can have neutron stars up to 2.5 solar masses, and then at 2.6 solar masses you start having black holes? Or is there actually this gap and the lightest black hole isn't until 5 solar masses and there's actually nothing between 2.5 and 5 solar masses? So that's something we're able to learn about by looking at the masses of all the gravitational wave sources we're seeing. Similarly, on the upper end, what's the most massive black hole? So in particular, we might think that there aren't stars that can make black holes that are 80 times the mass of our sun. Though we've seen black holes that are 80 times the mass of the sun in our sample. Very few of them, so you can see that the rate is very low at these masses between 60 and 80, but it's still there. And so are those black holes actually made from stars, or perhaps they're made from something more exotic? Perhaps they're made not directly from dead stars, but actually from a previous merger of 2 black holes that then went on to merge again with another black hole. So kind of learning about where these black holes and neutron stars are coming from by looking at their masses. Another thing that we're able to study that I mentioned a bit earlier is the composition of neutron stars. So exactly how does stuff behave when we squeeze it down into such high densities? And exactly how dense are these neutron stars? So how much mass are we able to squeeze into how small a volume? So this depends on how neutrons behave and how the nuclear physics works. And so, and then in addition to that, when 2 neutron stars merge, they create these explosions. They don't only emit gravitational waves, they actually create these explosions that we can see in light, and you essentially have these 2 dense neutron-rich stars crashing into each other, which is creating a lot of heavy elements like gold and platinum. And I'll show here in this movie what that looks like. And this is just an animation of 2 neutron stars crashing into each other, but we also observed this happening. Back in August of 2017, we observed 2 neutron stars crashing into each other, and a lot of this ensuing explosive material that we could see in light across different wavelengths. And so that's what you see here from this merger. Then you have this explosion and these gamma ray jets go out. Then you have this kilonova material and this afterglow from the jet. And so this is actually, people pointed their telescopes at this and were able to see everything from the most energetic light to radio waves, and are actually still observing this system, and it's still emitting all of this light in radio waves and in X-rays. So it's very exciting. Okay, I think this is my last example of things that we're able to learn about from these gravitational wave sources, which is on the largest scales, the cosmology of our universe. So one kind of fundamental question we want to know is, how old is the universe? How big and how old is the universe? And we can study that by looking at, for example, this so-called Hubble diagram. So the universe around us is expanding, right? Like, imagine the surface of a balloon that's being blown up, so every point on that surface of the balloon is moving away from other points on the surface of that balloon. And what this means is that when we look out at stuff in our universe, it seems like everything around us is moving away from us. And the things that are further in distance from us are moving, their speed away from us is faster because the universe is expanding. And we're able to measure the rate of this expansion with these gravitational wave sources. So that's because we can measure the distance of the source from the gravitational waves really directly, and then we can also measure its speed or its redshift from observing what galaxy it lives in, and measuring the light from that galaxy is telling us about this redshift. And so we can make this diagram, and here, so there are kind of large error bars because this is just for one event that we have this. But by having a lot of these events, we're actually able to measure how fast is the universe expanding at different distances. And from a diagram like this, you can imagine kind of going back in time, right? We're on this balloon that's being blown up. Now, reverse that to when there was just a single unblown up balloon, and that's the Big Bang. So by measuring how fast the metaphorical balloon of our universe is being blown up right now, we can learn about how long ago was it that the Big Bang happened, and how old is our universe. So kind of answering some of these deep questions just from observing these gravitational wave sources. So in conclusion, there's a lot we can learn from gravitational waves. These gravitational waves are carrying information about the motion of massive objects. And in particular, the gravitational waves that we're able to detect right now are from these collisions of black holes and neutron stars, which produce these loud gravitational waves that we're able to look for and detect. The way that we detect them is with these interferometers like LIGO and Virgo. And by analyzing these gravitational wave signals, we're able to measure the masses of the black holes and neutron stars, their spins, the distance and sky location of the source. And by having this catalog of black holes and neutron stars that's growing very rapidly, we can learn about things like stars, the origin of heavy elements, the age of the universe, and also make many unexpected discoveries, because this is still just the beginning of this field. So with that, I'll conclude, and I'm happy to take additional questions.
I have a question. Sorry.
Yeah.
So kind of two questions, actually. So I'm assuming we have, just like the observable universe, we have a event horizon. It would be the same with the gravitational waves too, right? Because it's coming at the speed of light, so we can't see beyond a certain distance. Is that accurate to say? In other words, we wouldn't be able to get any information beyond our horizon. Is that correct?
Right. Yeah. And for these gravitational wave sources, or at least like the black holes and neutron stars that I talked about today, we're probably limited not just by the observable universe, but also by the time that the universe started making stars, which took some time after the Big Bang for the universe to make stars that were then able to form neutron stars and black holes. So yeah, and well, actually, it sounds like, you know, something that's really far away and kind of far in the future of our technological capabilities, but these planned next generation of gravitational wave detectors that will come after LIGO and Virgo, so just like kind of like one technological leap in the future in 10 to 15 years, those will actually be sensitive enough to observe black holes out to farther away than we think they exist in our universe. So we'll actually be able to say, like, when did the universe start merging black holes? So that's really exciting how kind of quickly we're able to go from not being able to observe any black holes to seeing every single black hole in the observable universe.
So that actually made me think of another. So do you think there will become a standard candle for a black hole or for these types of mergers?
What do you mean by that?
Like we know there's a certain supernova type 1 supernovas.
Yeah.
So that became a standard candle for measuring the universe.
Mm-hmm.
Would there be some kind of a measuring stick we would be able to derive from gravitational wave study?
Right. So there are standard candles in astronomy because there are things that have kind of a distinct light curve, and just from the light that they emit, we're able to tell their distance, how far away they are. We actually don't need, so gravitational waves are, from merging black holes, are a much more natural way of doing that. They're actually, in analogy to standard candles, they're called standard sirens because of the like sound analogy. And that's because we don't need to kind of understand anything too deep about these mergers. Just from the amplitude of the gravitational wave signal, we know how far away the merger happened. So with something that emits light, that's really hard to do because you see something that's really bright and you don't know, is this just a kind of normal star that's close by, or is it a very bright, intrinsically a very bright star? So same with something that's very faint, you're like, is this a bright star that's really far away, or is it just a faint star that's close by? With gravitational waves, we actually know from the gravitational wave signal how loud it intrinsically is from the frequencies. So we can just look at the frequencies and read the masses, and so we know how loud it intrinsically is. And so how loud or quietly we hear it in our detectors, the amplitude that we measure of the gravitational wave signal, just tells us about the distance because it decays inversely with distance. And so the distance is very naturally encoded in the gravitational wave signal. It kind of doesn't require any additional calibration. And so that's why we're able to kind of make these measurements like this that you would otherwise make with standard candles, but we're kind of able to do it in this independent way with gravitational wave sources.
Sort of my last question. Sorry, everybody. So if there's other masses relatively close, like let's say within a couple of light years away from these merging objects, would the gravitational wave do any kind of displacement of that mass or shearing effects? I mean, is it that energetic, or is it, I mean, it sounds like it's really super energetic.
It is,
for that
it's
fraction
super,
of a second.
yeah, it's super energetic, but it couples very, very weakly. So it's a lot of energy, but the ripples themselves are so tiny. So they don't really have an effect other than the gravitational wave memory effect, which I talked a bit about. But it's, yeah, again, it's very tiny. So the actual like stretching and squeezing effect is 1 part in 10 to the 29 for the loudest gravitational wave sources. So it's a lot of energy, but it just couples so weakly and kind of interacts so weakly with anything else. So, yeah, wonderful.
What specific part of the gravity wave Super Bowl is your interest, and what did you do your dissertation on?
Yeah, great question. So basically, in the stuff that I talked about, I work a lot on this part. So within the collaboration, I do a lot of these analyses where we call them population analyses, because we're looking at the demographics of the black holes and neutron stars that we observe and thinking about their masses, how many heavy ones are there compared to light ones, are there features that we can see, like are there a lot of them at around 30 solar masses for some reason, and kind of trying to think about the astrophysical implications of that. So how can we connect this with what we know about massive stars in different galaxies and things like that. And then also actually this cosmology analysis that I talked about, that was another part of my dissertation, is measuring the so-called Hubble parameter, how fast is the universe expanding, the expansion history of the universe, and what can we learn about the universe on the largest scales. I didn't work so much on this neutron star part, but there's a guy back there who's shaking his head. I'm embarrassing him. Reed Essick is an expert on neutron stars. So yeah, we work together. But yeah, I guess this first and this third point are things that I worked on. Yeah.
Yeah, when I was looking at when you were showing the frequency change and when it gets higher, okay, I understand that, but there's got to be a lot of pairs of objects out there spinning together. How do you separate them from each other when these things are going on at the same time?
Yeah, that's a great question. So there actually aren't. Okay, so first of all, we are only sensitive to the most extreme objects, so like black holes and neutron stars that are going around each other. And then if you look at black hole mergers in our universe, they actually aren't that common. So I guess a second point is that we're also, right now, with our current sensitivities, we're only able to observe things that are relatively nearby. So billions of light years away may seem like quite far away, and it is, but we're not yet sensitive to every black hole merger in the universe. So they don't happen. So the ones that we're actually able to pick out of our detector noise, the ones that are loud enough, right now are only happening like once a week. In the future, we hope that we'll be sensitive to every binary black hole merger in the observable universe. And then you might worry that, well, they'll be happening on top of each other, but they're actually not merging that frequently. So they wouldn't, if you could hear every black hole merger in the universe, it would only happen like once a second or something. So they wouldn't go on top of each other. For neutron stars, because we're able to detect them for longer, basically they're merging at higher frequencies. So when they enter our detectors to the time they merge, they're in band for over a minute. And so then also their merger rate is higher. So then we might have signals kind of on top of each other. But it's usually won't be like 10 signals on top of each other or 100 signals. It'll usually still just be a handful, so you can kind of start by picking out the loudest ones and then removing them and looking underneath the noise and things like that.
So would these studies give us any more insight into like dark matter and dark energy?
Yes. Yeah, so in a few ways. So gravitational waves are really opening up our observational strategies of the universe in like all the ways. So all the questions that we had about the universe we're now able to kind of get this new angle into this and this new perspective. So for dark energy is what's causing this accelerated expansion of the universe. So the universe is expanding, and it's actually expanding at an accelerated rate. And we have no idea why that is. We just call it dark energy. But gravitational wave signals are, first of all, allowing us to better measure exactly this accelerated expansion through this kind of standard CIERA analysis. So dark energy starts to dominate at around, not here, but if we can detect things at kind of larger distances, actually where we have most of our binary black hole mergers, that's where in this expansion history you really get the effects of dark energy. And so we can just better measure that. Also, many theories for dark energy have to do with something about our theory of gravity being a little bit wrong. And that can explain dark energy. And gravitational waves are a really unique way to probe that because they are gravity. They're giving us access to measuring gravity in this completely new way. And so if something is a little bit wrong with our theory of gravity, so for example, if in a lot of theories for dark energy, you would have gravitational waves somehow experiencing additional friction as they travel to us because something is a little bit off in space-time that we don't understand. And by measuring these gravitational wave signals at different distances, we can start to put constraints or actually measure this friction term. Or in a lot of theories, gravitational waves would travel at a different speed from the speed of light. So we've actually measured by having this neutron star event where we measured both gravitational waves and light from the same collision. Those gravitational waves and that light arrived within a couple seconds of each other on Earth. So from that measurement alone, we're able to say gravitational waves and light travel at the same speed to within 1 part in 10 to the 17. And so that actually ruled out this large class of dark energy explanations. And so, yeah, definitely gravitational waves are probing dark energy. They also are probing dark matter. So one possibility for what dark matter is that there's black holes of different masses that are what dark matter is made of. And these black holes are not kind of this picture of dead stars that I've been painting. Maybe black holes were created in the very early universe during inflation, these primordial black holes. And there are theories that say dark matter is actually just these primordial black holes. And so by looking at the demographics of our black holes, we can kind of say, are these primordial black holes? There's also this idea that dark matter is what's this axion particle, this kind of new type of particle that may form in clouds around black holes. And you might have these dark matter clouds around black holes that would affect the spins of the black holes because it would essentially suck this energy out of the black holes through the spin of the black holes and cause black holes to spin down. And again, that process is something that would emit gravitational waves that we can look for. Yeah, so kind of many different ways tying into dark matter and dark energy. Yeah, there's a question here in the back there.
Yeah, so LIGO works by detecting spatial distortion, right, in this wave. So theoretically, it's also a time wave, right? So is it possible to take two really accurate atomic clocks and synchronize them and measure that difference as opposed to building these, really long tunnels?
Yes.
Is it conceivable or is it possible?
Yeah, no, yeah, it's definitely possible. I think what also you're describing is another type of gravitational wave detection method that we use is through pulsar timing. So we use pulsars, which are these spinning neutron stars around the galaxy, which are very precise clocks. And by, essentially timing all these, so that's like a galactic scale interferometer. By essentially timing the arrival of these pulses from these neutron stars, we're able to tell whether, basically through looking at the correlations in the timing offsets, we can tell whether gravitational waves have passed through the pulsars. So yes, that's actually one thing that's already being done. That kind of measurement takes a long time because you have to build up like your timing measurements over many years, and so they've been collecting data from a bunch of these pulsars around the galaxy for 15 years now. They have almost detected gravitational waves. I think in the next couple of years they will have said that they've detected gravitational waves from these pulsars, and so the thing to look for there, that's the International Pulsar Timing Array is that collaboration, and there's the Nanograv, which is the kind of the North American sub-collaboration of that. So I think that's another kind of existing gravitational wave detector that's making use of these precise pulsars, clocks. I think there was a question in the back. Yeah.
Yeah, so thinking of this analogy again of space-time being like a fabric, correct me if I'm wrong, Dr. Fishbach, is it true that then looking at it in terms of the whole universe and the expansion of the universe, and you have to have some elasticity, you have an analogy to elasticity to space-time, and then in order to prevent it from becoming so inelastic or stretching out so much that you have it, slow down and maybe a contraction eventually. Do they describe it as perhaps being under compression at the time of the beginning of or just after the Big Bang?
I think the analogy about like space-time being elastic is helpful. I mean, one way to think of like gravitational waves being so weak, even though there's so much energy, is that space-time is very stiff, and so it's hard. It takes a lot of energy to cause the stretching and squeezing of space-time. I'm not sure I totally got the part about the Big Bang.
Well, I think I read that someone posited, someone theorized that it was sort of, in terms of elasticity, that everything was sort of under compression at the time of the Big Bang, either because of the black holes that were primordial or whatever, so that effectively if you put it into the elasticity analogy, it was compressed and therefore it was wanting to expand, and it didn't have to be being stretched at first, it was taking the compression and turning it more to its normal state.
So we don't really understand the Big Bang and like exactly we don't, within the theory of general relativity that we have for gravity, we can't describe things that are too small, and we know we can't because this theory of gravity that we have is incompatible with the theory of quantum mechanics, which governs things on the smallest scales. So I think exactly what happens at the Big Bang when you go from having something very tiny that we know we can't describe with our theory of gravity to having space-time on large scales where we know that our theory of gravity is a good approximation. Exactly what happens on those tiniest scales, like at the beginning of the universe or at the center of a black hole. We don't have a theory for that works. So I think that sounds like some like proposed theory or way of thinking about it. But I think yeah, I think we don't, there's no like agreed upon universal theory that we have that we can use to explain those types of problems yet. So, yeah.
So how many events in total have we seen like this between like black hole mergers and neutron star mergers?
Yeah, so it's getting a little bit difficult to count them because we have some where we can say, that's really loud, that's definitely a gravitational wave signal. And some that are kind of quiet, and we're like, is that a gravitational wave signal or is that noise? We think it's, 60% is a gravitational wave signal, well, 40% chance that it's noise. So you'll see different numbers for this. The numbers I use are 69 events that are two black holes colliding, so around 70 binary black holes so far. 2 binary neutron stars, so the one that we also detected in all this light and the gamma ray burst and the kilonova in 2017. That was the first binary neutron star, and then another one which we detected only in gravitational waves, and then a handful of neutron star black hole mergers, so around like 3 to 4.
Is that it? Is that everybody?
One more, and then I'll
Yeah.
shut up. So your graph where you had the event frequency versus the solar masses,
Yeah,
there's a local maxima there, right?
yes.
So does that tell you anything interesting about what's going on?
Yes, probably. Yeah. So we're still trying to figure that out. So we first fit this. Yeah. So we do think that there's an excess of events that have masses between around 30 and 40 solar masses. We're not quite sure what causes it. We think that it might be due to a type of supernova explosion that happens. Basically, when you have stars where the core of the star is between 40 and maybe like 120-ish solar masses, it undergoes this type of explosion called a pair instability supernova, which just means that at those masses, you have the photons in your star, so the light in your star is spontaneously producing electron-positron pairs and escaping your star, and that photon is otherwise supplying pressure to counteract gravity. But in this case, those photons are just disappearing as these electron-positron pairs, and you have this type of supernova explosion that can lead to these pulses of mass being lost. So you essentially, it leads to this very violent ignition of oxygen in your star. And sorry, this is quite a detailed explanation, but the thing we think it might be due to these pair instability supernova, which would basically cause stars that would otherwise make black holes in this mass range lose a lot of mass, and so they might form black holes that are in this mass range. So that it means that you might take black holes that would otherwise merge here and have them merge at around 30 to 40 solar masses instead. And so that might cause this kind of pileup here. But that's just one explanation, and so we're still looking at other things in addition to looking at the demographics in terms of masses, also looking at the spins and seeing like, are the ones here also spinning differently from the ones up here, and things like that. So, yeah.
Is that pretty much it, everybody? Thank you, Doctor. Really appreciate it.